Okay, hello everyone. So today we're going to complete our concurrency control discussion, and we're going to focus on multiversion. So last few times, again, we looked at multi-granularity locking, then we switched into optimistic, and we looked at a couple of variants there. We looked at timestamp. Now, kind of looking at multiversion. And again, this has become closest to what we have been studying in your project and then in Alston as well too. So basic idea, something you've already should be familiar with, is a multiversion and its timestamp. In Elstor, we haven't really mentioned anything about timestamp, but that's an interesting usage of in concurrency control. So that can definitely be utilized. In the paper, we do talk about how to exploit timestamp as part of the concurrency control. But the sort of the classic multiversion timestamp CC or concurrency control is that anytime you want to add something new, you make a private copy. And once you are committed, you make your private copy visible. So the old version, you make a new copy of the data, or also you do copy on write. So first you make a copy. That copy could be local, no one can see it, and only at the time of the commit could be visible. Or as in Elstor, that local copy is not really local because everybody can see it, and other transactions who are reading it, you need to kind of notify them somehow that this is something that is currently being written, so it's not finalized. And one way to do that, for example, in Elstor, is that if you have the start time column, at a time when you write the tail record in the start time column of the record, since you don't have the start time either, you would only get the start time at the commit time when the transaction is actually committed. So there you can put the transaction ID. So somebody's reading that tail record, they read the time, the start time, they realize, oh, this is a transaction ID. And you could potentially have a lookup table, like an internal memory lookup table that says, given this transaction ID, what is the status of it? Is it ongoing? Is it aborted? Is it committed? And if it's committed, what it is, the timestamp that it was committed. So that's something that the user can look up once they see an ID. And once the transaction is committed, you can go back and swap that transaction ID with the actual start time. And that start time will be the commit time. That's something that can be done as part of the commit phase, or it can be something done lazily at a later point. So those are kind of different choices to handle that. But that's in terms of Elstor. But now coming back here is in the multiversion, you add this new version of version O, and this version O of the object O can point to the previous version, O prime, and the O prime can potentially point to even an earlier version. So that's the idea, you're maintaining all the versions. So really what we've been doing with the Elstor, it's a multi-version. We have retained every single version. This could be useful for to reduce the contention between the reader and writer, and making sure that the reader can always proceed, but they may be blocked. And if you remember in the 2VCC, we talked about speculative read. And speculative read, essentially, they get a commit dependency on the writer, meaning that if the writer is currently in the certification phase we talked about, the reader can come in, read that record, but they will be notified, or they become aware that this write hasn't been fully finalized. So they need to wait for that, the writer to commit before they can be certain that what they've read is a valid version of the data. So they're not blocked. So they're not blocked, or they're not blocked from proceeding, but their final commitment of the read could be delayed potentially. So that's just the basic idea of the multiversion. Again, that's something you've already seen. And so one way to now actually implement the concurrency aspect of it, again, we're going to utilize what we've been talking about till now, is that each version of the object has a write timestamp and a read timestamp. And the write timestamp is the transaction time of the transaction that wrote it, so that becomes the write timestamp. And the reader is the last transaction who read the record. So again, with the example that I gave earlier with the else store, using the start time, so we're only maintaining, you can think of it as a write timestamp. So that else store example, we're not really retaining any read. We're only retaining a write timestamp. And versions are chained backward, and again, that's something we do in else store as well. And at least in this classical model, you kind of distinguish between the reader and writer. It's not necessary, but that's something that was utilized in this particular model. And well, the writer can write objects and the reader will never write anything. So at least for one thing is that you don't have to, if you know a transaction is a reader, for example, you can think of it as that if there's some concurrent transaction and some concurrent transaction should potentially see any data from one particular transaction that is ongoing. And if you don't know if this is a reader or writer, other transaction may kind of have to wait to see what happens, what the fate of this transaction is going to be. But if you know if it's not going to change anything, then that will simplify some of the decisions to whether wait for such transaction or not, or whether this transaction could potentially have any side effect in terms of the data that it's going to change. And again, you declare it in the beginning, whether it's a reader or writer, so kind of something that is known a priori. And we need to look at two things. How does the read work? How does the write work? So basic sort of show you this diagram is that the blue is an old version, the new is a newer version of the record, T is a transaction that wants to read, and it has a timestamp T. And this is essentially a timeline. So now how does the read and write works? For each object that you wanted to read, you find the newest version that is visible to T. That means the newest version that its timestamp is smaller than T. So therefore this is going to be visible. This is written by a future transaction or even a newer transaction. So the write of this transaction should not be visible to this T. And so that's the read. And the timestamp of the transaction is assigned at the beginning. So at the start time, that essentially becomes your also the commit time. So the time that is assigned when the transaction gets executed. Again, this is this particular model of concurrency, this multi-version concurrency control. So you find the newest version, and the newest version you find, okay, this is the blue one. So the blue can be read. And assuming every object has some initial version, therefore the read can always get to read something as long as there exists a record to be read. But again, as I mentioned, if, for example, let's say this green one wasn't there, and this blue one does exist, however, it's written by a transaction that hasn't yet committed, then the T can go ahead and still read this, and this is the record that needs to read. However, it needs to wait for this transaction to be committed before the outcome of the read or the outcome of this query can be reported back to the user. So the reads are pretty straightforward. Any question? Okay, so now let's look at the writes. So again, let's look at the diagram first to make sure that we're on the same page. So This is, again, the timeline of the write. So this is the previous version of the record, written at the old timestamp. This is a newer version of the record, or the newest version that is written by the green transaction. This particular version has been read by some transaction. There's a read timestamp of that. And this is the new transaction that is coming in, this read transaction. So let's see how the write works. So first, before I want to write something, I want to read the initial version. So how does that work? We'll follow the same read protocol that we talked about in previous slides. So if I'm from the read transaction, I find the largest version of the record that is visible to me. That means the largest version of the record, which is its write timestamp of that record, is smaller than the transaction, my transaction. So now to write an object, so first we find this newest version, which is in this case is V, and the timestamp of this version is smaller than the timestamp of the transaction T. So we found our version, everything's good. Now, if the last read version of this record, the RTS, so if the last transaction who read this record, its timestamp is smaller than T, so maybe I'll pause here. What does this mean? So what does this condition really mean? Any thought? Why would I be concerned about such condition? Where are we kind of heading to with this condition? Why would I be concerned about a transaction who read this blue version? Well, you're concerned about it because you want to make sure that whoever read this blue transaction, you're not going to violate the read to ensure the read repeatability. So, and the read time, so this is read by some transaction, and that transaction timestamp is at this point. But since these read timestamp is smaller than the T that is writing right now, that means the version that T is going to be writing, it's not going to be visible to this transaction anyway. Therefore, this write will not cause any repeatability, because even if this version existed, as far as this transaction is concerned, they're still going to read the blue version because this red version is not going to be even visible to it. There's no violation of any repeatability of any read. So then, in that case, we can make either a local copy or a copy that is global but is somewhat tagged in one way of is some way tagged that other transactions are reading or writing it, they know that this is an uncommitted record. So there will be this CV, this the copy of the V. So this becomes the version that this read transaction is installing. The write timestamp of it, of course, it will be the transaction time, and also the read timestamp, because this is also, technically speaking, has already read this version. So both the read and timestamp, read and write timestamp initially start sets to the transaction who wrote the record. And this write can be buffered until the commit time, meaning that it's not physically become visible, and only at the commit time we make them visible. So that's one way of doing it. The other way is that we kind of do with the out store. We can make it visible, but somehow you can mark it as that this is a transaction that has not been committed. An example of how you do that is kind of what we started the class with. If I in the start time, because the start time of this version which is going to be the commit time of this transaction. If at that start time, I just put the transaction ID, and the reason I put the transaction ID because I don't know what the commit time is and because it hasn't been committed yet, then the reader can use that information to figure out whether this is an active transaction or a transaction that is already, its fate has been finalized. So now if kind of the other part of this condition, if the version that I'm going to write, this red version, could have been potentially visible to some other ongoing transaction, therefore this write is rejected and the transaction needs to abort. And the reason for that is that if this read timestamp, this blue arrow was here, that means as far as this transaction, these other transactions is concerned, this red version should have been read. This red version would have been the newest version visible to this transaction. But and since when this blue transaction read the record, this red wasn't available, and now it is. So either we're going to lose serializability, meaning that that blue transaction is not going to see what was expected to be seen, or if that transaction is kind of still ongoing and it may read the record again, well, you will also have the repeatability read problem as well too. So either way, you're not going to have a serializable schedule. So if this condition is not met, then the write will not be accepted. And if you talk about in terms of the 2VCC kind of sense, is that, or let's say actually before 2VCC, in terms of 2PL, if there was a transaction, blue transaction who have read this version, they're still holding a read lock, so this write of the red would have not been allowed. In terms of 2VCC, is that the read would have been allowed, but the write certification would either have failed or the write certification needed to delay. Of course, in the 2VCC, we're not really talking about timestamp, but that's kind of one analogy to connect the two approaches. Any question? All right, and that's timestamp. So that's kind of one classical way of doing multiversion in combination with timestamp in order to order the transaction. Yes.
So, I mean, is it at all possible for two transactions to have the same timestamp if, say, they requested the current time at the same time on multi-threaded application?
Yes, that's a good question. So the timestamp becomes essentially a global bottleneck in a sense. In fact, time is the most difficult thing to manage. So before kind of getting to the notion of the time, usually when you, not usually, when you, oftentimes when you're requesting a timestamp, it becomes a monotonically increasing counter. So every time you request it, the counter goes up. So you will never assign the same timestamp to two different transactions. So that issue would never happen, the issue that you raised. You're not going to assign the same timestamp.
Okay.
So, but that's only if we're talking about if you have a single counter. So if you have a single counter, I can always increment this counter before I allow anybody else to read it. So every time the counter is read, it's also incremented. So that ensures that no two transactions can get the same timestamp. Of course, if you're now talking about distributed, then you have multiple counter, then that problem of synchronization of the counter becomes much more difficult. So even in the central setting, having a single counter could potentially become the bottleneck of the system, because as fast as you can generate that single counter, because every transaction needed, that may determine how fast you can execute transaction. So that becomes single point of contention. And that's essentially the notion of a time, because you want to make sure that you have a synchronization in the notion of time. You talk about, and this is something we're going to cover in the next lecture or next two lecture, kind of extending this to distributed transaction. And there's, you need to maintain, in a sense, a synchronous clock in a distributed transaction. And again, the notion of time becomes the most expensive and the most complicated. Transaction processing is all about time, one may argue. So if you can solve the problem of time synchronization very efficiently, then you can execute transaction very efficiently. And so if you make it a single counter, everybody needs to access the single counter. Now, if you make it a multiple counter, then you need synchronization to make sure these counter are either always up to date or they are within some window of each other. So that becomes that interesting time synchronization problem. Any other question? So in terms of isolation level, again, we've really kind of been focusing on the serializable and on the true serializable, or in fact conflict serializable. And usually is mentioned serializable in the database literature or in any database product. When they say serializable, they really mean conflict serializable. And if you remember, the difference between conflict serializable and just a regular serializable is that the conflict serializable doesn't concern about non-conflicting transaction. Non-conflicting transaction can be done in any order. It doesn't really affect the result. It's only the conflicting operations or the conflicting transaction that we need to maintain a consistent ordering among the conflicting operation. So serializable, always underlying it means conflict serializable. So if you have serializable isolation level, sort of the strongest that the database will provide, you will not going to have any dirty read, meaning you're not going to read any data that it's uncommitted and later maybe even aborted. You will going to have repeatability of the read. So if you read something and you read it again as part of your transaction, you guarantee to always get the same answer. But you also shouldn't have any phantom problem. When we talked about predicate locking, index locking, or different mechanism in order to ensure that there's no phantom. And the problem with the phantom is that even if we use a strict 2PL locking, we lock all the object that we're going to access, well, it's possible that a new object gets inserted that would have been visible to us if we rerun our query. So that's the issue of the phantom that we talked about last week. So that's the highest level of serializability, isolation level. One level lower is the repeatability. And the key difference between the repeatability is that it's not concerned or it doesn't prevent phantom. So strict 2PL is a repeatable isolation level, but it's not serializable because it could be phantom. So you need additional mechanism to ensure that it becomes serializable. Read committed. So this is something that we talked about even in 2BCC, or this is also something we talked about when we talk about extending our indirection to committed or uncommitted. Read committed basically says is that it just reads committed value. It never reads any uncommitted, but there's no guarantee in terms of, for example, if all the updates of a concurrent transaction will be visible or not. So it's possible that you have two transactions. One of them is read-only, let's say, one of them does updates. So it's possible that the read-only only sees some of the updates of the writer transaction and doesn't see all of them, and that's okay. But under serializable, it's all or nothing, because under serializable, transaction is running in a serial order and the transaction is all or nothing. So either the changes, all of them are visible or none of them are visible. So the first serializable, the last row definitely prevents it. Repeatability, of course, prevents that, minus the phantom, but the read committed does not prevent it. But it ensures what is read. It's not something that later would be invalidated. So that's the only thing that it essentially prevents. And the read uncommitted, well, this is the lowest level of the isolation. This just basically, even if it allows reading a data that later could be aborted, but it's okay. The read is going to continue and it's okay for it. And there are, again, applications for this. Is that, for example, if you're doing a large aggregation, you're reading millions of records or maybe billions of records, if even a few dozen or few hundred of those records that you read is later aborted, it may not, for example, affect your average. It may not affect your sum. So the overall effect of it, it will be minimal. So, but then if you're running your query under the uncommitted mode, you can run it substantially faster because you essentially don't have to worry about any locks. So you can run things that much faster if the application can tolerate those inconsistencies. Of course, if you're running a banking application, and well, it would be very difficult to tolerate any inconsistencies. Even in the banking, they don't always run at the most strict level. An example of that is if you somehow, within very short time span, go to two ATM machine and you only have $500 in your account, you could potentially overdraft yourself by $500. You only have $500 in your account. You go to the first ATM machine, you take 500, and you quickly go to the second ATM machine, you take another $500. There is a lag before the data is fully gets propagated, and so you could potentially have a negative balance of 500. Of course, then there is what is referred to as compensation method that deal with these anomalies post-transaction. For example, what your bank will do says, okay, you did an overdraft charge and you will be charged $30 fee. And of course, if you do it probably more than a few times, then they may even close your account. So that would be a compensation method in order to prevent it, or in order to discourage of such activity. But what really they did, they reduced the isolation level in order to speed up the execution. Or again, you may have also already experienced this, and the airlines are notorious for this, of double booking. Not every agency or not every website that sells airline seats, they actually have those seats available. So for example, if there's Expedia and there's a couple of other airline and this plane has only 100 seats, they may kind of allow to 120 seats to be sold. And the reason they do that is, okay, maybe there's some lag and delay between all these different agencies who sell the seats. And so by the time they all get propagated to the system, it's going to take time. So they don't want to, so they want to speed that up. And also they may also say, okay, well, on average, maybe 5% of people who bought the seat, they're actually going to cancel by the time, or they don't do show up. So why do we have 5 empty seats? We try to give that away to others. So you may go to the airport and they have double booking, and somehow that flight becomes full, and now they have to do a compensation. So they say, okay, can you take the next flight? We give you $1,000 credit. So any inconsistency that caused in the execution or in the transaction, for example, of buying the seat, there's going to be a lot of headache after. I mean, you're going to have unhappy customers who have a double booking, or now you also have to pay $1,000, maybe $500 of credit to them, in addition to rebooking them. So there's others, so you have to, so there's a financial cost to it, and also there is other penalty, again, unhappy customer, for example. But so serializability will prevent all of that, but serializability, maintaining serializability, especially in such distributed system, is not always possible. And relaxation is allowed, but they need to be dealt with. More of those relaxation you allow, the more and more complicated the application becomes. If you go through all the way to serializable, you really simplify the application, because the application doesn't have to deal with these type of scenarios. And some of these scenarios, for example, the one that I described, they're not even just within the application, they go far beyond the application. You have to probably go back and forth with the customer, settle on what that credit is going to be, and there's human involved, and it becomes a much lengthy process. The actual transaction may have taken sub-second, but to deal with the aftermath of this transaction, not only you have to maybe spend the thousands or so, but there's probably hours and of lines, and there's a lot of human involved. There's also the salary of the people who have to deal with to resolving this situation, and so again, it will have an impact. So that's different isolation. Any question? That's it. So summary, we looked at strict 2PL, we looked at 2PL. Of course, we have been, before that, we looked at 2VCC. We looked at also quick. So we've been looking at optimistic, we've been looking at deterministic. Deterministic is such as quick, that you kind of deterministically know what the database, what the transaction going to read and write. So you kind of plan them, and you essentially run it almost without any concurrency control during the execution. And of course, then we looked at more classical optimistic 2PL, and then we looked at the timestamp and the multiversion. And you can, if especially with the locking, or anytime that you wait, there's a possible for deadlock. So we talked about detection, is that you draw this dependency graph, and if there's cycle in the dependency graph, then there's a potential deadlock, and then you need to decide which transaction to abort in order to break the cycle. Or you could have preventive measure, and the preventive measure, simple one, is that like a no wait 2PL. You basically don't wait, you use a non-blocking, you never wait. And if you never wait, well, you're never going to have a deadlock. Or you always wait for a younger transaction, or you always wait for an older transaction. So as long as you maintain a consistent ordering of how you hold block or resolve blocks, then you can avoid deadlocks. The other way of avoiding deadlock is that you take lock in a certain order. So always you lock the first record, then the second record, then the third record, and so on. Of course, locking things in order, it also means that you know the full set of the transaction, the full set of records that you need to read and write a priori. Going back to that deterministic database case. Again, it works for certain application, but it doesn't work for every application. And then if locking is the central to the design, and this is something that you will do for your third milestone, the standard is the strict 2PL and having a lock manager, then you really have to spend time and make sure your lock manager is efficient, because otherwise quickly becomes the bottleneck. And interestingly, although lots of effort had been to make the lock manager efficient, but as long as you had the disk, accessing to the disk on the path of the transaction, which was potentially in order of milliseconds, the lock manager did not become as prominent or as a main contention or a main bottleneck. But the moment especially in the early 2000s, that the memory size become large enough to hold most of the transactional workload, then meaning that you're not going to have much of a read and write to the disk, the lock manager once again became the central bottleneck. And well, the lock manager is the main data structures supporting the concurrency control. So that means the concurrency control again became the main bottleneck. And so again, in the last 20 years, has been lots of interesting development in the space. And again, as we said, talk about different locking, and it's important in terms of whether it's you do a coarse grain versus fine grain has a lot of impact on the performance. And then we talk about index locking that helps with prevention of phantom, but also you need locking for your data structure to make sure that if you're adding a record and your B tree needs to increase or decrease in its height, there's further race condition that is happening within the data structure as well too. And the one thing that also we distinguish in database, and this is only for database community, is that locking a record, we talk about locking, but when we lock a page or when we lock our data structure, we call them a latch. So we say we lock a record, but we latch a page, or we latch our tree, or we latch our buffer pool. So anything that is not that's on the data structure, it's referred to as a latch. Anything that refers to the record itself or to the data at the sort of the either record level or table level or range level, they mention it, they call it a lock. In other field, the word lock and latch used interchangeably. In the database, that distinction is made between the two terms. And this is something that already some of you kind of the granularity of the lock, whether you do page level locking or you do record level locking. So of course, the finer grain locking that you do, it allows more concurrency. But the finer grain you do, that means you potentially have to manage more locks. And so you need more efficient way of managing them. So for example, there's been a couple of questions on Piazza, is that, well, at the end of my merge, can I just, once the merge is done, can I just momentarily lock my entire buffer pool in order to update my metadata? So that becomes a really coarse level locking. Sure, it's easy to implement, it's much easier to test, much easier to maintain, but it really reduces the overall performance, because during that time, that entire, for example, the buffer pool is locked at that very coarse level, essentially all the other transactions are on hold. And not only that, in order for you to lock the entire buffer pool, you actually need to wait for all ongoing transactions to first finish, because you cannot just, if already others are using it, you cannot just override their logs. Sure, you can abort every concurrent transaction that is happening right now and then go lock the buffer pool, but probably it's not the best choice either. But really, you have to put a pause on accepting every single new transaction. And then you also have to put a pause, making sure all the ongoing transactions are completed, then get the lock on the entire buffer pool, and then do any kind of switches. So again, any type of coarse level locking will have a performance penalty. But again, it's simpler to implement. It's basically just waiting for stopping new transaction, waiting for new existing transaction to finish. And once that condition is met, have exclusive access essentially to the entire database. And now you can just run whatever needs to be run without any low level synchronization. So almost no synchronization, because it becomes a single threaded at that point. So that's So those are would be the trade-off in terms of the granularity of the log maintained. And even there are multiple hierarchical we talked about. We can lock at the record, page, table, database, or I mean, buffer pool will be essentially because a single buffer pool used across tables. In a sense, buffer pool is almost like the lock in the entire database. And the reason we will have this higher granularity lock is that if a transaction really needs to change all the data or needs to read all the data as opposed to requesting individual locks and thousands of millions of individual locks, you hold a higher granularity lock. So that's a much more effective way of handling that. So that was our multi-granularity, and then again, the different optimistic CC and the different isolation that we also talked about as well too. So this final slide of serializability, repeatability, read committed and uncommitted read. These are standards that are defined by SQL 92, and they're referred to as degree of concurrency or degree of consistency. So, and again, we talked about timestamp, and then we also talked about the multi-version timestamp today as well too. So that wraps up this chapter on concurrency control. And this is essentially was the last lecture that we dedicated time to concurrency. So next lecture, we're going to talk about distributed transaction, and we're also going to cover a bit on blockchain and sort of how the field is going to move forward, perhaps in the coming years. And then after that, we're going to shift on more some of the more classical topics, especially we're going to look at query language. So we're going to look at relational algebra, then we're going to look at SQL, and if time allows, we're going to look at simple optimization of SQL queries by use of indexes and so forth. So that would kind of wrap up the semester. So get a solid understanding of how the data is stored, how the data is protected through concurrency, and some of the newer fronts of databases such as blockchain, and then how the query language works. So we know how to store the data efficiently, we know how to protect the data, we know how to replicate it in a sort of democratic and decentralized way through blockchain, but then how do I query the data in terms of what kind of questions, what kind of query can be asked post to the database? What is the expressiveness of the language and different representations, relational algebra and SQL. So far for the assignments, for the LSTOR, we kind of assumed a simple interface of just read and write, or a key values, so key value interface, and a sum interface, an aggregation, but kind of adding more complex operator on top of that. Sort of that would be potentially the second continuation of this course if we were to have it. But at least you understand in terms of the expressiveness. So we're going to spend the last 3-4 lectures to those topics. Okay, any question? If you have any question, I'll be around. Otherwise, have a wonderful day, everyone.